Based on what we did in the last two videos, it may not be readily obvious why Lebesgue's approach is superior to Riemann's approach. Riemann took a partition of the domain and Lebesgue took a partition of the codomain, but it seems even by this roundabout method, Lebesgue eventually came to a step function just as Riemann. But this is true for only this particular example that I have shown, not true in general. In case of Riemann, we worked with approximations whose set we denoted by script t. These were step functions with finitely many steps. In Lebesgue's case, we used approximations from the set that we denoted by script s. These were simple functions, that is, functions that can take only finitely many possible values. What should be readily obvious is that script d must be a subset of script s, because if you take a step function with finitely many steps, then over each step it takes the same value, and since there are only finitely many steps, it can take only finitely many possible values. For example, in this case, this is one value, this is another, this is a third value. This step has the same height as this step, so they have the same value. This is another value and this is another value. But what may not be that readily obvious is that this inclusion is a strict inclusion. So these are not the same. There are simple functions which are not step functions. This particular simple function is indeed a step function, but there are many simple functions that are not step functions. Let us take a look at one such example. We consider this function, the so-called Dirichlet function. We have taken it to be defined from AB to R. Whenever x is a rational point inside the interval AB, I take fx equal to 1, and whenever it is irrational in that interval, I take it equal to 0. I claim that this function f is a simple function, and that is obvious because it can take only two values, 1 and 0. Any function taking only finitely many values is by definition a simple function. However, as we can easily guess, this is not a step function with finitely many steps, because had that been the case, you can come up with a partition such that over the same interval it will take some common value. But in every interval there are rationals as well as irrationals, so it cannot be always 1 or always 0. So we see f is not in script t, and that proves d is a proper subset, a strict subset of script s, because we have already seen that script t is inside script s. The situation is somewhat like fitting things inside a mold. Suppose we have these two molds and we are trying to fit plasticine into them. So in this case, when you fill it up with plasticine, you can fill it up well because of its smooth nature. But if you try to fill this mold with plasticine, you will not be able to reach into these nooks and corners, because plasticine is a pretty inflexible thing. But however, if you take the same mold, but instead of plasticine, you use plaster of Paris, which is just liquid, in that case, you will get a much better fit, because the liquid thing will reach out into all nooks and corners. Now that is exactly what happens when we are using Riemann's approximation. Riemann uses his approximations from script D that are not that flexible. So if the function is rather complicated, certain nooks and corners cannot be reached into. But this is what happens when you are using Lebesgue's approach, where he is using simple functions that are more flexible. So it can of course reach out into all the nooks and corners that can be reached by script D, but it can also reach out into more complicated functions. Remember that in both Riemann's approach and in Lebesgue's approach, we are always trying to take the supremum of all the approximations from below and trying to equate that to the infimums of all approximations from above. The difference was from which set were these approximations chosen. Suppose that in case of Riemann, I call them SR and IR, then I always have SR less than or equal to IR, because all these things are below my curve and these are above my curve, and whenever these two things are same, I will say it is Riemann integrable and the common value is that of the integral. Now in case of Lebesgue, I shall call the corresponding sup and inf SL and IL. Again, by the same reason, I have SL less than or equal to IL. However, observe that SR is the supremum taken over everything in script D, whereas this is supremum taken over script S. Since this is a larger set, so this supremum must be greater than equal to this supremum. But of course, these things must be less than this, because both these things are under the curve and both are above the curve. So I have SR less than or equal to SL, SL less than or equal to IR. Now again, when you look at infimum, the infimum is taken over a larger set. So infimum over a larger set cannot be larger, it can only be smaller. So IL will be somewhere here. So you see SL and IL are sandwiched between SR and IR, which means that if SR and IR are same, so if Riemann is happy, the function is integrable according to him, then SL must also be equal to IL, which means Lebesgue must also be happy. The function must be integrable according to Lebesgue as well, and the value must match. However, it is possible that SR and IR are wide apart, but SL and IL are same. So it is possible to have a function which is Lebesgue integrable but not Riemann integrable. Formally, we have this theorem: if a function is Riemann integrable, it has to be Lebesgue integrable, and in this case, the values must match. However, it is possible to have something which is Lebesgue integrable but not Riemann integrable. In this exercise, we are going to see precisely one such example where I give you the same function, the Dirichlet function. It is a known fact that f is not Riemann integrable. You have to show that f is Lebesgue integrable with the integral equal to 0. Just a hint that this is already a simple function, so all that you have to work out is length of this set. And remember, it's a countable set, and we of course have length of any singleton alpha is 0. Since it's countable, so we can somehow arrive at the fact that this length is also equal to 0.